In the next section, I want to show you one concrete problem and make the point that randomization can indeed be more powerful than any deterministic algorithm. I wanted to show you one concrete example of this for one to make to show a concrete adversary, because I think this is insightful for other problems too, and also to drive home that point that randomization is really doing more than just making algorithms a bit simpler. So I'll try to avoid detailed discussion of what the randomization formally means. We'll come back to that. I should mention that this is not an NP-hard problem that we're working with here. And so also the randomization is not going to decide between exponential and polynomial or anything like this. The difference is smaller, but we can prove that it exists here. And the example is the selection problem, selection by rank, the thing that QuickSelect solves. So just to recap, the input is an array of numbers or arbitrary objects that you can do pairwise comparisons on. And you're also given a number k, and you're trying to find the element that would be in that given position k if the array was sorted. That's a convenient way of saying that you want the kth smallest. It's a bit more specific or a bit more precise in case there are duplicates in the input. Then if you say the kth smallest, does that include duplicates? And what about all the elements that are equal to the kth smallest? You can avoid all that if you just say it's an element that could be in position k in the sorted list. Makes discussions here a bit easier. But for all that follows, you can assume that the numbers are distinct, and then it's really the same. Special cases that we'll focus on is for k is n², then we're looking for the median element. So the element where half of the input is smaller and half of the input is larger. What you learned in undergrad is this QuickSelect algorithm. Different ways to write it, but here's the one with a loop. You're maintaining a range of the array where you still have to work in. Initially, it's everything. And as long as that's not empty, you pick a random element from that range. You partition that range around that element, everything smaller to the left, everything larger to the right. And then there's three different options. Sometimes you're lucky and the pivot element you picked is exactly the one that has rank k or is at position k in the end. Then you will eventually return it. Otherwise, if the splitting position where the pivot landed is too far to the right, then you have to continue searching on the left. K is still left of that. Then you adjust the upper bound, and the other one is symmetric. I suppose people remember what this works like. Really, the point here is if you don't do this random choice, the algorithm has a quadratic worst case, just as quick sort, the more famous cousin of this. And the other bit is the algorithm is really simple. It's simple to write down, it's simple to code, and it works really well. But it needs this randomization to be robust. Now you can show that it takes linear time in expectation, and you can compute much more about this, determine exactly how many comparisons it does, and so on. But let's not go there yet. Now, I also should mention that you can also solve the same problem deterministically. And the kind of algorithm you would have seen for that is the median of medians algorithm, where you group elements in columns of 5, sort those, then take the middle third, the third smallest of each 5, recursively find the median of that, and then partition with that guy. Substantially more complicated than this code for sure. Still very doable. but also much slower in practice if you compare the two. Okay, so far so good. So let's take a slightly closer look at what happens here and what we can do in the extreme cases, or in beyond these simple algorithms. All of what happens is within theta of n. We can do expected costs linear in n, and we can do deterministic cost linear in n, and there will be a lower bound linear in n. But the constant in front makes a difference here. So first of all, there's a lower bound for any deterministic algorithm, assuming it's comparison-based as for sorting. So a deterministic comparison-based algorithm for finding the median has to use roughly 2n comparisons in the worst case. Okay? That proof is a bit tricky. What I'll show you is a simpler version that gets a slightly weaker bound. Annoyingly, it's yeah, we'll see. So the same statement, just that now we have 1.5n comparisons. Or more precisely, we have n minus 1 and n minus 1/2. The reason why I split this up this weird way is that's what you get from the proof. And so let's design. Let's prove this. And there's essentially two parts. There's two types of comparisons. There's some comparisons which are necessary from an information theoretic perspective, which means if the algorithm doesn't learn about the outcome of these comparisons, it cannot be sure that the output it produces is correct. So in our case, we want to output some element x and claim that this is the median. So if I'm outputting this element x and claim this is the median, I, as the algorithm, I have to have proof of that. Otherwise, some mean person modifies the input in a way that makes my claim wrong. It's a bit like the typical argument in this direction. An adversary argument would be, to find the minimum of n elements, you have to look at every element. Otherwise, if there's an element that you haven't even looked at, that you have not compared with anything else, then the adversary could make this much bigger or much smaller than the other elements, depending on what you claim the minimum is, and it will fool you. It will make your claim wrong. In the same way, you have to show that there's comparisons with the other elements, say n is 11, and the way we'll draw this is like a Hasse diagram for partial orders. So an element with an arrow down means this one is bigger than this one, and this one's bigger than this one. And it's a partial order, so this is transitive. But what I've shown you here is the certificate that x is a median. So the claim is, unless the algorithm has learned a partial order of this form, where your element x is in the middle, and there's some way to say these 5 elements are larger than x and these 5 elements are smaller than x, unless you have somehow learned the information of such a partial order, you cannot prove that your median is correct. If any of these edges is missing, I can modify the input so that your claim becomes wrong. Okay? if you think about it, what this was for sorting, you can also make the case if you want to sort a bunch of elements, you have to learn which one's bigger than the others. So you have to arrange them in some linear order. That's the largest, second, smallest, blah, 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 down to the smallest. So for n elements, the certificate is just n-1 comparisons. But we know for sorting, we actually need many more comparisons. So the certificate comparisons are not always sufficient. And here as well, there's n-1 comparisons that you have to do to certify that the median is correct. But sometimes, and most of the times, you need extra comparisons to find the right certificate. And for sorting, we know this gap is really big. For medians, the second type of comparisons are non-essential comparisons. These are the ones where in hindsight, you know, I actually wouldn't have needed to do that comparison. If somehow someone would have told me what comparisons to make, I would not have done this one because it doesn't help me certify the median. So the thing is here, if I tell you this is the median, if I already give you that guess, and then you can compare that median to all the others. It's like one round of partitioning in quick select, and you immediately find that that's correct and that's the answer. Then you only need n-1 comparisons. What we'll try to prove is that in general, or in the worst case, it's not possible to make the correct guess without additional comparisons. In sorting, you do that lower bound with decision trees. There's just too many different things you have to determine, you have to distinguish. For the median, this wouldn't work. The number of different things is basically just n. There's n different choices for the median. And maybe you learn which ones are smaller, which ones are bigger, but you don't get this, this big gap for an n log n. So how can we still do, against deterministic algorithms, some bound on non-essential comparisons? So a non-essential comparison is one that's not part of the certificate. So in particular, any comparison that compares an element that's at the end strictly larger than the median to another one that's strictly smaller than the median, it doesn't help us find the median. Okay? The L and S are these sets, so let's define M as the true median. L is all the elements that are larger than the median. Likewise, the smaller ones. And by the way, we know that these are of the same size, right? But that's it's not needed here. So any element from L and any element from S, if I compare those two, I kind of, at the end, I already know the one in L will be bigger than the one in S. So that comparison is wasted. But what we'll play now is adversary. We're given some fixed deterministic algorithm that will do its thing, but it can only access the elements via pairwise comparisons. So at some point, the algorithm has to pick two elements and ask which one of those is larger. And at this point, we jump up as the adversary and will construct the input comparison by comparison, trying to fool the algorithm to do as much work as we can make it do. That's the general pattern that adversaries against some algorithm always take. They always have this kind of form. In the specific case here, what we do is we maintain the elements of the input in three sets. Two will be S and L, where we've committed that this element will eventually be smaller than the median. So you should think about it this way. We initially have the n elements lying around, and they're just uncolored marbles. And we can decide what they are ordered like. But we don't have to fix that choice until the algorithm asks us about specific comparisons. We can change our mind along the way if we feel like it. We just can't make it a lie what we've told the algorithm in the past. We have to stay consistent to the previous answers. So initially, every element will be in U, undecided. We don't know yet, or we haven't committed yet to that element being eventually smaller or larger than the median. And so now, whenever the algorithm asks a comparison, asks a question, which of the two is smaller, we check if we've already decided where the elements are. So the algorithm asks us, is x less than y? Now we check if x and y are not in the same sets. Then we answer according to the small one elements are all larger than the undecided ones, and these are all smaller than the large ones. Okay, that decides the comparison, and that's all we do. If the elements are both in S or both in L, then it doesn't matter. We just answer something according to an arbitrary order of these elements that we somehow fix. You could say by the time they entered this set. And the last option that still is possible is that they're both in U. Okay. In this case, we say arbitrarily that one is smaller, one is larger. And now we put x in the small set and y into the large set. And what have we done with this with this step? Well, we've generated a non-essential comparison. Because at the end of the day, neither x nor L will be the median, and they will lie on opposite sides of the median. So this comparison that the algorithm has just done is turned into a non-essential one by the way we answered. Okay? And so that's all we do. How expensive is this for the algorithm? We always need the n-1 certificate comparisons. The algorithm has to learn those, no matter what it does. That's this part. And for the remainder, because every element starts initially in U, and we only move elements when we do this last step, for the algorithm to learn about the true median, well, we only reveal the median really at the very end if there's a single element left in U. And this is kind of automatic by the first case. As long as there are elements in, if the algorithm is stupid enough to do comparisons where both elements are in S or in L, then it pays more, and we don't even charge it for that. But it has to get all the elements out of U to make progress, because we're never going to reveal useful information to it before that. The useful information only comes from the first case. So it has to get all the elements out of U, all but the true median. And so it's n-1 elements that have to go. But for each step, we take 2 of them, put them away. So it's n-1 half that we get as comparisons. Right? With each comparison that we generate, 2 elements are moved away from U. So we create 1 comparison for A. So against this adversary, any deterministic algorithm will have to pay the certificate comparisons and at least n-1 half additional comparisons, which we turned into non-essential ones, but the algorithm couldn't have known. It's out of luck. This proves the 1.5n. There's a sequence of works that improves that bound up to the 2n, which is where it currently stands. Whereas the best upper bound is 2.95n, and it's unknown how many comparisons you really need for deterministically finding the median. It's kind of unsatisfying that we don't know this simple question. What I wanted to say is how to get the higher lower bounds is by making this adversary more sophisticated. Here we immediately put x and y from the unknown sets, 1 up, 1 down, and we harvest 1 comparison. The generalized forms of that keep some order within U. Unless that compares only a few elements, you can keep them around and then do a lot of case distinctions on what the adversary should do, and you can make the algorithm pay a few extra comparisons. But that gets super technical, and I think it's worth doing once, but not digesting in a lecture. The key idea is these kind of reasonings of maintaining the elements in some sets and choosing when to answer what. I wanted to go through this proof because I think it makes blatant obvious that if the algorithm is randomized, a lot of this trickery is harder to do. It's you can't really you can't really force the algorithm to make the same kind of now I'm struggling because this lower bound is also true for randomized algorithms. And I think this specific construction, there's nothing that stops you from doing that against randomized algorithms. The more sophisticated algorithms that maintain this partial order, they make this harder. But you can at least see from this proof that designing an adversary might be easier if the algorithm has to commit to a fixed sequence of comparisons up front. The last bit to drive home is randomized algorithms. The one we've seen, quick select, it doesn't actually beat this bound. In expectation, you need 3.39n with quick select. But that's just because the algorithm is kind of wasteful and simple. You can do better. And I don't want to discuss the algorithm in too much detail because that leads us too far into analysis. The key idea is to take a large random sample from your array. And the rough size of the sample is this n to the 2/3. That's a big sample, but it's a little O of n, right? So with this sample, you can do a lot. In particular, you could actually just sort it and make the algorithm simpler. It's a bit more efficient to recursively select from this. The idea is that you, suppose you want to find the median. So here's your k. You pick a large sample from this array and find two elements whose ranks are just left and right of k by a small amount. And then you do one big partitioning step to narrow down the list to this tiny space. The partitioning costs 1.5 n comparisons because you're doing it with two pivots. You compare every element to one of the pivots and those that are larger to the other one. And so because these are so close together, it's essentially half of the elements that you have to pay a second comparison for. So it's 1.5 on average. And then you can work out that all the rest in the algorithm is little o of n work because you're working on a small sample or you're working on cases that are unlikely to occur. What this needs is knowledge from statistics about how likely is it that this estimator for the median that we get from the sample is off by so and so much. So I don't want to get into this in detail. But the bottom line is that you can do randomized median finding in 1.5n comparisons. And that's strictly less than the lower bound we've seen cited, the 2n comparisons that you need deterministically. Okay. So at least in terms of this constant factor of the number of comparisons, randomization gives you strictly more power. And here, I guess you can see it as you take away power from the adversary to make you pay extra comparisons by hiding your next steps. Okay, that was a bit of a little detour deep dive in one concrete problem where you can work out this separation. What we want to come back to next time is what happens on NP-hard problems. Can we get more dramatic improvements from randomization there? And for that, I want to first define things properly. There's a few interesting things from just the mathematical side that happen that I think is worth setting straight first.